Welcome back. In this video we're going to talk about the vector equation for an ellipse. We're going to begin by recalling the general scalar equation for a circle centered at h, k with radius r. Recall that we said that that equation was given by x minus h squared divided by r squared plus y minus k squared divided by r squared equal 1. If we bring the r squared over to the other side, we get the equation we know and love. We're going to analyze this equation in terms of distances and the scalar r, because the equation for the ellipse really comes from changing this r to a general a and this r over here to a general b. To begin, let's look at what happens with this equation if we go along the center lines. We did this in the last video, and now we're just going to generalize. So suppose that I assume that I'm at the y equals k line. So that's a horizontal line along the center. So this would immediately imply that my equation is given by x minus h squared divided by r squared on the left-hand side and 1 on the right-hand side. And this would mean that the distance from x to h is exactly r squared. Recall that in order to get rid of the square, we take the square root, and this would be x minus h squared square rooted, and then the square root of r squared. Of course, r is assumed to be a positive number, so then when we square it and square root it, we get back to the same thing. This would be x minus h in absolute values. And then this would mean that we have one of two things. We have either x minus h is the negative of r, or x minus h is the positive of r. And then this correlates with two values. Either we go from the center and we move r units to the left, or we go from the center and we move r units to the right. And these are actually both ordered pairs. This is the h minus r k, or the x coordinate of this value would be h plus r k. Okay, so that's what would happen is if we started with this equation and we went along the y equals k line. Let's look what happens if we go along the x equal h line, which would be a vertical line through the center of the circle. So the moment that this happens, our equation for the circle simplifies to y minus k quantity squared divided by r squared on the left and 1 on the right. You can repeat the same process at home, and I encourage you to do this for yourself. Never trust a teacher. I'm going to simplify the steps, not because I believe they should be simplified, because I want you to immediately test yourself to see if you can recreate that math. So this would mean that we have y minus k is negative r, or y minus k is positive r. And this would correlate with 2 points. We go to the center point k and we go r units down along that vertical line, or we go to the center point in the y coordinate k and we go r units up, and both of these points would then be h comma k minus r on the bottom side, or h k plus r on the top side. Let's go ahead and graph what we've done here. I encourage you to recreate this graph on your own. Here is the vertical line, here's the horizontal line through the center. So we would call this the y equal k line, because every point on this line has a y value of k. Notice when we go r units to the left, we get the exact point h minus r comma k that we said we would. When we go to r units to the right, we get h plus r comma k, and then again up and down. The reason that I want to show you this is we can come up with a general parametric equation or vector valued equation for any point on this circle. So notice that we have a few different relationships. One, the value of the radius is given by the square root of the length of each of these. So if this is x comma y and this is h comma k, the length of this is a and the length of this is b. But notice we can actually calculate those lengths explicitly because the difference in x values from h to x is x minus h squared, and the difference in y values from k to y is of course y minus k. And we talked about that in videos from lesson 2, I believe it was. So the whole idea here is that we have a is x minus h and b is y minus k. That's how we would calculate r. And we have something more here. We also have that when we look at the angle theta, we know that the cosine of theta is going to be adjacent a over radius r, which another way to say this would be x minus h over r. And then we have finally that the sine of theta would be, well, maybe we need to actually see this. It would be opposite over hypotenuse. So this would be b divided by r, which of course is y minus k divided by r. And the moment we have these two equations relating cosine and sine and x and y, we can actually start to generalize any point on our circle will satisfy the relationships governed by this particular equation. So this is x minus h would be r cosine of theta, which immediately would imply that x was given by r cosine of theta plus h. And another way, remember when we were talking about vector equations, we generally like to use the parameter t to represent time. So this would become r times the cosine of t rather than theta plus h. That would be the x coordinate of any point on our circle, given in parametric form. The y coordinate would come immediately from here. We would have y minus k equals r times the sine of theta, which would immediately imply that y is equal to r times the sine of theta plus k. And since we like t to be our parameter name, this is r times the sine of t plus k. The parameter name t, the reason that we like it so much is because it correlates with this really cool thing in life called time. So that's the only reason that we do that. And this immediately gives rise to a general equation, vector valued equation for a circle, where this would be x of t, y of t. And then notice we would have something that looks like this. X of t was given by, maybe we want to say h plus r times cosine of t. And y of t was given by k plus r times the sine of t. So this is what we call the general vector equation for a circle. Circle centered at h comma k with radius r. Let's use this vector equation for a circle to begin our discussion of both the scalar equation for an ellipse and a vector equation for an ellipse. To produce an ellipse, we generalize. And I want to create an analogy. The analogy is like this. A square is to a rectangle as a circle is to an ellipse. Squares require that all distances along the sides are equal. This is what we call the one norm. The one norm of the length is equal to the one norm of the width. Rectangles allow different one norms. They're kind of a weighted one norm. Your length can be different than your width. Circles are measured in terms of two norms. The two norm of the distance between the center and any point on the circle is constant everywhere. In the ellipse, some of your distances along the x direction can be weighted differently than your distances along the y direction. It's not a pure two norm in the sense that it actually comes from a weighted inner product. This is well beyond the scope of Math 1C. You would barely touch on this in your introductory linear algebra class, and then you would get really into it if you went up into upper division linear algebra and graduate level analysis. So, okay, but the equation for the ellipse goes like this. We still have a center point, so this is going to be called an ellipse centered at h comma k is given by a scalar equation x minus h squared divided by, instead of r, we're going to let this one be called a, and then here we have y minus k squared, and instead of the same r, we're going to let this be called b, and we'll let this be 1. And the reason that this is really important, of course, we have the assumptions that a and b are non-negative real numbers. You would even hope that they're positive if you want to have something interesting, but I guess we have to be general. We call A is what we call the length of the x semi-axis, and B is what we call the length of the y semi-axis. We'll talk about this more as we get into it. In order to fully understand this equation, instead of working in generality to begin with, I'd like to do a specific example and then generalize from that example. Here we go. So let's look at an example, and we'll start with the easiest case, an ellipse centered at 0, 0, with x semi-axis length defined by the value of 2, and the y semi-axis length defined by the value of 5. This ellipse has equation, and we're going to call this the scalar equation, not the vector equation, because it's going to be written in scalar terms. Here we go. We would have x minus 0, since h would be 0 and k would be 0. And we'll go ahead and make the algebraic simplifications in just a second. So this is x minus 0 squared divided by 2 squared plus y minus 0 squared divided by 5 squared equal to 1. Okay, that comes directly from the definition that we just introduced, and this of course would be x squared divided by 2 squared plus y squared divided by 5 squared equal to 1. And then we can do an individual analysis of the points along the horizontal line through the axis and the vertical line through the axis. So let's start first with the horizontal line for the axis. Let's set y equal to 0, which would immediately imply that x squared divided by 2 squared is equal to 1, which would mean that x squared is equal to 2 squared, which, when we take the square root of both sides, this becomes x in absolute value, because the square root of the square is an absolute value, would be 2. And then we have two cases. Either x is negative 2 or x is 2. And remember that each of these cases corresponds with a ordered pair. Here we have the ordered pair negative 2 comma 0. And then here we have the ordered pair 2 comma 0. That's what happens if we move through a horizontal line passing through the origin. Let's see what happens if we move through a vertical line, or in a vertical line passing through the origin. Here we would have y squared divided by 5 squared equal to 1. And with a little bit of analysis following the same template that we did up here, this would mean that the absolute value of y would be 5, which would mean we have two y values. We have the negative 5 and the positive 5. And these are both actually ordered pairs, where the x value of the ordered pair is 0 and the y value of the ordered pair is given as such. All right. Unfortunately, I didn't prepare a beautiful graph, so you're going to have to kind of sit through an ugly one. When we look at the interpretation of this, here we'll assume this is the origin, which means this is the x, this horizontal line is the y equals 0 line. And then here, this vertical line is the x equals 0 line. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then we could go the same here. Maybe we go up to 6, and we go down to 6. So here, what we saw on that last page was that the 2 points along the horizontal line were positive 2 and negative 2, and then the 2 points on the vertical line were positive 5 and negative 5. And notice we have this kind of oblong scaling. The distance along, this is why we call the length of the x semi-axis. This is actually quite deep. I can't help but riff here. Ellipses are so powerful in mathematics. There is so much of advanced mathematics that are based on this. Orbits of satellites. We have a concept of quadratic forms. I mean, I could teach a 12-week course on the value of ellipse as an introduction to the world. So it's kind of fun. The reason I say that is how fun we get to see this in Math 1C finally. Jeez Louise. So here we go. A is equal to 2, B is equal to 5. That's the length of the x semi-axis. If you looked at the length from the center to the external point of this ellipse, you would have that length was equal to 2. And that's a semi-axis because the entire length of that x-axis from outer point to outer point is 4. Half of that length is the semi-axis, which is 2. The length of the y semi-axis is the one in the y direction, and that length was 5, and that was directly governed by the equation for the ellipse. We, of course, could generalize this to any point x comma y, and maybe we'll do that in the next video. I think this video is getting kind of long. Let's switch over to Mathematica and graph this. Recall that the general equation, x minus h squared over a squared plus y minus k squared over b squared equal to 1. This is an implicit relationship, not an explicit function. The moment we know that it's an implicit relation and we want to graph it, we're going to use contour plot command, which will go look something like this. If it was an explicit relation, we would just use the plot command. Okay, so let's go switch to Mathematica, use contour plot to graph a general ellipse. Here we are in Mathematica. We're going to go ahead and plot an ellipse using contour plot. To do so, I need to define a center. Perhaps let's start with center 0. We'll start with y value of the center is 0 as well. And then we'll define the semi-axis. I think in our last example we said that a was 2 and b was 5. And then my claim is because that was an implicit relation, we want to use contour plot. It's in 2D, so we're not going to use contour plot 3D, obviously. So here we're going to comment our code always. Okay, the equation for the ellipse we said was x minus h. We're going to go ahead and square that quantity, so I can control square, and then we're going to divide that entire square by a squared. So that was the semi-axis length for the x direction. Why don't I just be lazy? Why don't I be efficient? That's how mathematicians try to make it sound beautiful by being lazy. And then remember that we said that this was equal to 1. In contour plot, we put the double equal sign because Mathematica is literally going to test this for truth. Double equals produces, so here's an example. 1 double equals 0. Oh, that's a false statement. 1 double equal 2 divided by 2. That's a true statement. That's a logical truth value. So what Mathematica is going to do is it's going to test all the points x and y that evaluate as true. And that's why we're using that double equal sign there. Here we determine the x range and the y range of our plot. So I'm going to be a little bit more generous. I already know that my center is going to be at 0, 0, and the largest distance I'm going to move from there is 5. But I might want to move my center around a bit for pleasure purposes. So I'm going to go from -10 to 10. And then here we go from -10 to 10. So there's our center. Oh, I never answered the question how to put the origin through. I don't really know the answer to that question. Shall we try to see? So let's say that I wanted the origin to go through. Let's go ahead and see. Let's call the command. So I want to go ahead and ask about contour plot. Here I'm going to go into the documentation center. So there's a bunch of documentation on this. It has details and options. Let's see if it has anything about axes. Yeah, I just want to show you a little bit about how to do this, right? Do you see anything about axes? I don't. Let's look at some examples here. Let's see if they do anything with axes. Yeah, that's okay. What you're seeing though is this is actually how I get a lot of inspiration for coding. When I try to find information about something, I very often use this double question mark. So I'll come back to that later. I don't really need to do that right now anyways. Let's go ahead and graph the center though. So I'm going to go ahead and show and then end the show command down here. And I'm going to put a graphics in this sucker. And the graphics is going to be a point. So I immediately open and close the braces, open and close my brackets. I think we said that the good point size, at least for these type of videos, was 0.02, I believe. And then I'm going to graph the point. Well, let's call this point C for center. And we'll let C be h, comma, k. So I'll graph the point C. What's it complaining about? Okay. What's really cool about this is I can change C now. Let's maybe move C 4 units to the right and -3 units down. And let's have the x semi-axis be 4 and the y semi-axis be 1. So it's going to be like a football. Aha! Should we do something really exciting? Should we like let this be like 8 perhaps? Whoa! And then we'll move this up to be +2 and this one to the left -2. Wow! Do you see it? It's pretty cool how quick that happens, right? In future videos, we'll talk about the vector equation for ellipse. Those are kind of fun. See you there.